Hey, you guys, here's your second installment of the second half of chapter 5 about gases. I had last time I didn't talk about it, but proof of atmospheric pressure. It's funny when people say, well, how do you know? How do you know there's gases around you? Well, all you really have to do is fan your face with a piece of paper, right? And then as that happens, it blows your hair around with gases. Well, and not to mention the wind. I don't know if you guys here in Colorado, we can get some pretty good winds due to differences in pressure in weather. So you get differences in pressure, and that air has to move in order to equalize pressure. So that's why we get those crazy winds sometimes. So let's talk about gas stoichiometry. Stoichiometry has to do with cooking, right? It has to do with how much you have of your reactants and then how much of your products are going to be created from that. Now, in this chapter, we're talking about gases. So we're going to utilize those parameters of gases like pressure, volume, amount, and temperature to kind of bring that all together, because some of our products are gases and some of our reactants are gases. So when we are thinking about stoichiometry, this might look a little, look familiar. When we're talking about amount in chapter 3, a lot of times we're talking about grams, right? Grams to moles to grams. But now we can do volumes, volume to moles to volume. Because remember that volume can be, if it's a gas, can be determined if you know the pressure of the system, if you know the temperature of the system, and the amount of the gas that you're dealing with. And also, as an added bonus, if a reaction is taking place, like the whole thing at the same temperature and pressure, that the volume ratio thing shows up. Whereas if you have 2 volumes of a product, a reactant, and if it's 1-to-1 ratio, you end up with 2 volumes of product, and you don't have to do really any calculations besides a mole ratio calculation. But it's called a volume ratio. So let's do an example here. What is the volume of carbon dioxide gas produced at 23 degrees Celsius and 0.8 atm when 3 grams of sodium bicarbonate react with acetic acid according to the following equation? So this is a fun equation here. This is baking soda and vinegar, which makes a gas and bubbles. I guess if you put soap in it, you could get some bubbles and make your like volcano. But as far as the product here, we got carbon dioxide, which is the only gas. We have liquid water is created, and we have aqueous. This is sodium, and then this is acetate. Remember the formula for that. You could also write acetic acid as to be H, C2H3O2. And then when you write sodium acetate over here, it's NaC2H3O2. And remember, acetate is a -1 charge and sodium is +1. So anyway, let's do this problem. If we have, the question is, what's the volume of CO2 produced? So we know how many grams we're starting with, so we can go grams to moles using molar mass and moles to moles using a mole ratio. And then now that we know the number of moles, we can use PV equals nRT to get the volume. So this really isn't any different than normal stoichiometry. Grams to moles to moles, and then you see how that cancels out, and that's going to give me the number of moles of carbon dioxide, and then I use PV equals nRT, just like I normally would. So this is a tool in your toolbox that you can use to calculate the different parameters of a gas. And it looks like everybody cancels out nicely, and we should end up in liters. And that's how many liters of gas would be produced at that temperature and pressure. Because remember, if you change that temperature and you change that pressure, you're going to have a different volume. So try fun sheets number 10 and 11. That's all about stoichiometry. And don't forget about the volume ratio thing, which is what is coming up right here. This is the volume ratio idea. So when we talk about volume to volume, if we have a balanced chemical equation, that can give us information as far as the number of volumes or moles created. Now, if they're at a constant temperature and pressure, I said the same temperature and pressure doesn't change, like this whole thing remains at a certain temperature and pressure as the chemical reaction continues. This volume ratio stays in effect. So if I have 1 volume of NH3, I will make 1 volume of NO, and that's the end of it. That's the answer. If I have 4 volumes of NH3, I will make 4 volumes of NO. So if I try fun sheet number 12, there's an example like that in there. Let's talk about Dalton's law of partial pressures. Dalton's law is related to the fact that if you have a mixture of gases, that mixture of gases creates a pressure as if there was only one gas. Now, if this has to be a volume and temperature or constant, but actually it doesn't, because let's go on here. Let's look. Here's a pressure of one guy. Here's a pressure of another. If you combine them, the pressure will be combined. Now, you might think that that's kind of obvious, but it wasn't when this was first being discovered and experimented with. So these different numbers here add up to give this one. So that's Dalton's law of partial pressures. That's this definition down here at a constant volume and temperature. Again, I don't think this really matters, because if I change the volume and temperature, this would still be true, but then the pressure might be different. That's all. So if we mix two gases like A and B in a container, you can see that this is the ideal gas equation, but this ideal gas equation is like being specific for gas A, and this one's being specific for gas B. So if this pressure is A and this pressure is B, you add them up, you would get a total pressure. And then I wanted to point out here, like if you have a P total here, then your P total would equal N total, and then your RT over V. So the T, total and total here, is what would make this true. Now this X here is called mole fraction, and mole fraction is the fraction of moles of a substance in a mixture. So here, the mole fraction of A is equal to the number of moles of A over the total number of moles of everybody. Same thing for X of B. Now it turns out that this pressure of the individuals is determined by the mole fraction of that individual times the total pressure, which is kind of intuitively makes sense, because the more there's let's go up to our figure up here, there's a P total here, and there's a certain amount of pressure that is contributed to that P total from the red ones and a certain amount from the green ones, and that is dictated by the mole fraction. So the pressure of A, which is red, there's a fraction of A in there, as defined by mole fraction of the total pressure. And P of B, same way. So this is Dalton's law of partial pressures, is stating that the individual pressures add up to the total pressure, and that the individual pressure is dictated by how much is in there. That's all there is to it. So let's do an example here real quick. If I have a sample of natural gas and it contains 8.24 moles of methane, 0.421 moles of ethane, or C2H6, and 0.116 moles of propane, C3H8. If the total pressure of all of them is 1.37, what is the partial pressure of just propane? So this is total pressure. If you just want propane, you can use the idea that individual pressure is dictated by the individual amount times the total pressure. So how do I know? I have to figure out the individual amount, and that's what we're doing here with this mole fraction. So an individual amount over the sum of all of them, it's like a percentage almost. So 0.0132 is the mole fraction, and if you want to do percentages, you could be 1.32%, but it's not exactly the same because it's not times 100. Then you would put your mole fraction right there times the total pressure. And that would give you the pressure of the propane alone in that mixture. And that's kind of difficult, because when you have a mixture of gases in here like this, they don't know that they're there. They just, that when I say they don't know, they might know. I didn't ask him. But if you have a little gauge here, like this is a pressure gauge, that pressure gauge is measuring the pressure, which is the collisions on the surface of that gauge, by all the molecules, not just one individual, or one type of molecule. So you can't, quarantine the red ones over here and the blue ones over here and the green ones over here. They're just all together. And that's why this relationship is important, because it enables you to figure out the pressure of one of them just based upon its mole fraction. Of course, you'd have to know the mole fraction. So try fun sheet number 13. That has something to do with this example. And it's talking about nitroglycerin. And nitroglycerin is an explosive. And when it explodes, it makes carbon dioxide, gas, water, vapor, which is a gas. It makes oxygen gas, and it makes nitrogen gas. That's why it's such a good explosive, because it makes all these gases, and those gases explode outwards and knock anything over in their way. So try fun sheet number 13 based upon nitroglycerin. Let's talk about collecting a gas over water. The reason this is important is because when studies were ensuing about gases, and they're like, well, let's collect the gas. Well, how do you collect it? Somehow you put your bottle here full of water, and then you invert it inside water, and then there's nothing, there's only water in this container. And then when this tube goes in here, the gas bubbles out, and then the water is pushed down and out. And this fills with whatever gas that you're collecting. But since you're at a certain temperature, there's some water molecules in there. So since Dalton's law of partial pressures says that this is a total pressure of all the said molecules or said gaseous molecules in there, that water is giving an erroneously high pressure. So that has to be subtracted out. So in this example, this is potassium chlorate being heated, and it makes oxygen gas. And that oxygen gas is what's being collected in this picture. So the total pressure is both the water and the oxygen gas. So how do we know how much water is in there? Well, it's been tabulated for us at different temperatures. There's a different vapor pressure of water that is the pressure of the water molecules above that solution. So as temperature goes up, it makes sense that more and more water molecules would be vaporizing, and that's why this pressure keeps on going up until you hit 100 degrees, which is the boiling point of water at sea level. And that's why the vapor pressure is 760 millimeters of mercury, which is equal to the atmospheric pressure at sea level. So that's why it boils. So if you think about a mountain, and here is sea level, and I'm boiling water down here. Here's a pan, and I have water in here, and I'm heating it with some red flames. It's going to start to heat up, and as it starts to heat up, there's a certain pressure of water above that surface of the water in the pan, and there's also a pressure pushing down at sea level that is equivalent, if we're at sea level, to 760 millimeters of mercury. So when the pressure of this water equals that, that means that it's equal and opposite, and that means it can now boil and get out of there. Before, this was holding it in, if you will. So either way, as far as Dalton's law of partial pressures is concerned in collecting a gas over water, we need to remember that there's a certain amount of gas, water in there, water vapor in there, that needs to be subtracted out. So as far as scuba diving is concerned, your book has a chemistry in action that talks about pressure and volume, and that if we increase pressure, we would decrease the volume and vice versa. So when you scuba dive and your body is going under here, the pressure is increasing on your body. And so that's why you can have some issues with surfacing too quickly, because the bubbles, if you will, that are in your blood of nitrogen can expand too quickly and end up getting like stuck in the joint spaces or something like that, it was called, and gives you what's called the bends, which keeps your joints bent or something like that. You'll have to check that out and read that. It's interesting stuff. So, and you want to be able to scuba dive with knowledge, and you don't go too deep. If you go too deep, you have to make decompression stops. So it's all based upon the gas laws. So let's talk about the kinetic molecular theory of gases. Kinetic molecular theory is the theory that gases move, that the molecules move. So gases this is the theory, that they're composed of molecules that are separated from each other by distance far greater than their own dimensions. So when I draw a box of a gas, and I just do that, they're separated. The molecules can be considered to be points. That is, they possess mass but have negligible volume. This is for an ideal gas. Number two, gas molecules are in constant motion in random directions, and they frequently collide with one another. Collisions among molecules are perfectly elastic, meaning they don't lose any energy. Gas molecules exert neither attractive nor repulsive forces, and the average kinetic energy of the molecules is proportional to the temperature of the gas in Kelvin. I feel like I should not have S there, but Kelvin. Any two gases at the same temperature will have the same average kinetic energy. And that's for, I don't know if you remember, your kinetic energy formula is 1/2 mu squared, where u is the speed of the molecule or car. I mean, I don't know if you remember from physics, kinetic energy is 1/2 mv squared. I think this is average. This stands for average. Remember the bar at the top. So as far as compressibility, the kinetic theory makes sense because they're mostly empty space, and that's why gases are so compressible. So as far as Boyle's law is concerned, since molecules are in constant motion, if you increase the volume, the number of collisions should decrease, and you should see a decrease in pressure if the temperature is to remain constant, because if it didn't, the temperature would increase. In Charles's law, molecules are in constant random motion. So if you increase the temperature of a gas, the number of collisions should increase, and you should see an increase in volume if the pressure is to remain constant. So what are these again? This one is in Charles' law. If molecules are in constant random motion, if you increase the temperature, the number of collisions should increase, and you should see an increase in volume. Up here, in Boyle's law, if molecules are in constant random motion, if you increase the volume, the number of collisions should decrease, and you'll see a decrease in pressure. And Avogadro's law, of course, the more gas you put in, the more volume result because you have more collisions. See, collisions is the key word. Collisions is the key word in kinetic molecular theory because they are moving. The molecules are moving and they are colliding with each other in the walls of the container. In Dalton's law of partial pressures, molecules do not attract or repel each other. So that means the gas behaves as if it was in the container alone. Hence, the total pressure is given by the sum. So since they don't attract or repel, that's part of the kinetic molecular theory. So Dalton's law of partial pressures substantiates that. So as far as figuring out how fast molecules move in a in a gaseous state, this was a really interesting little machine here. It was a way to create a gas, and then this vacuum pump would pull out the gas, and the gas would move. And as the gas would move, these were turning, and they were turning at certain speeds that was measurable, and it was be able to tweak it and say what speed you want it to turn. And as that turned, there was a detector on here that most of the molecules were showing a certain speed that was based upon temperature. So this worked because you could figure out, this was all geometry. I mean, these little triangles and everything. It was a geometrical calculation that was enabled you to figure out the average speed of the molecule. So how did that turn out? It turned out that as you heat up a sample, you get a larger distribution. So you wonder, if you look at this little curve here and that previous slide that we just saw, there were those circles. And that was a circle, and it showed all the dots, and the dots got thicker through here, and they ended up getting thinner out at the corners here. And that was a measurement of the speed. So if you got it really cold, you would end up with more dots in one area than you would out here. So this distribution curve is the distribution curve in here. So you might get a very narrow distribution curve, or you might get a really wide distribution curve. So you would think that the hotter it is, the faster they're all moving, and then you would get a really big, a lot all over the place. So as gases were heated up, they move faster, and you got a larger distribution curve. But if we had to change the gas that was in there, and you had chlorine versus nitrogen versus helium, and the temperature was held constant, you still got different distribution curves. And that was based upon molar mass. So the heavier the molecule, the slower it goes. So chlorine was the heaviest, so that's why its average was slower than the helium, which was the fastest. So that's what that's indicating there. Now I kind of messed up let me erase this here so we can see that what this is showing is called the root mean square, root mean square speed of a molecule of gas. And that depends upon the molar mass inversely, and it's directly related to the temperature. So the faster it goes, the bigger the T, the faster the speed. The heavier the molecule, the slower the speed. So this is just a way, this was the relationship that was determined by those experiments. So as far as diffusion is concerned, the gases diffuse. So it does make sense that that when you heat up a gas, it will diffuse faster. So all of these different relationships kind of work together. So gas diffusion, by definition, is the gradual mixing of molecules of one gas with molecules of another by virtue of their kinetic properties. Kinetic meaning they're moving. So when a gas diffuses through the air, it's bumping off of other air molecules as well as maybe the wall or whatever, and it makes this different, very erratic path. Oops, I messed it up. So this is kind of neat, showing how gases diffuse, and there's a piece of evidence here that shows the diffusion. This is hydrogen chloride. This is hydrochloric acid concentrated. But when you open the lid, that's why you got to be very careful with gases, especially concentrated gases, is that this is now leaving the bottle. And the hydrogen chloride gas weighs about 36 AMU. And then this is ammonium hydroxide. Now, ammonium hydroxide is NH4OH. But when you open the top, it's decomposing and ammonia escapes. And ammonia is a gas. If you have a cat litter box, you know what I'm talking about, right? So this is a gas, and it weighs 15, 16, 17 AMU. Now, what it looks like here is that, what is this evidence of this white cloud trying to indicate? Now, you might think, oh, it looks like the hydrogen chloride is moving faster than the ammonia. But that's not true. What's actually happening is that you notice this white solid, and what this white solid is that NH3, well, we can call it 4OH. No, I don't want to do that. I take it back. Because what's being formed here is ammonium chloride. So let's say NH3 meets in the air with a hydrogen chloride molecule. And then what you get is NH4, or ammonium chloride. And that is a solid. And so you see over here, we're already seeing some of the smoke, but it's not smoke, it's actually this solid ammonium chloride. And notice it's not on this side. That's because that ammonia left and it zipped right over there and was already forming that solid right around the mouth of the container of hydrogen chloride or hydrochloric acid. So there it is. And there it is. So as far as this diffusion, what this is saying is that the rate of diffusion of a gas is proportional to its molar mass. So if you have two gases, like you have a 17 and a 36, and that's the molar mass, if you know the rate of one, you could solve for the rate of the other. So I wonder if we could do that real quick, just for fun here. I just like to put these things in. Let's say M2 is HCl. And so I'm going to put that in here, 36. And then M1 is 17, the square root of that. And then I'm going to say R1 over R2. I would like to just see what the number is that we get here. If we take 36 divided by 17, and I take the square root of that, I get 1.45. Get R1 over R2 equals 1.45 to 1. Now, which one was R1? See, 1 is 17. So that means that R1, the rate of number 1, is 1.45 times as fast as 2, which makes sense because 17 was lower than 36. So effusion, we just did diffusion, which is diffusing through space. Effusion is the process by which a gas under pressure escapes from one compartment of a container to another by passing through a small opening. So this is effusion. So you have them all over here, and then some of them will get through there, which of course they will. But the relationship for that is similar to that relationship we just saw. But diffusion, it looks like T must have to do with time. So when we say times, see, it has to do with time. So effusion is gas going through a small opening. Diffusion is just through a big open space. So let's do this example down here. To illustrate, nickel forms a gaseous compound of this formula. What is the value of X given that under the same conditions, methane, which you know the formula of CH4, effuses 3.3 times faster than the compound? So if we know that if we call 3.3 times faster than the compound, you can use that as kind of that ratio that I did on the previous slide. So now we have the molar masses, And I'd like to put the molar masses, they're calling M1, I'm going to put it up here, 16. And M2 is unknown. See, we're trying to figure that out. We don't know what that is. Square root of that. And then I know, now M1 is on the bottom, R1 is on the top. So R1 is equal to 3.3. I'm going to try this here. R1 is 3.3 times R2 divided by R2. R2, yeah. And then that equals the square root of X over 16. And then can we just, the R2s are going to cancel out. And then we can solve for, because this is the square root is the same thing as something to the 1/2 power, isn't it? So if we square 3.3, let's see if I get this right. Squared, 3.3 squared, because I'm going to square both sides, because I'd like to get rid of this 1/2 power. So if I 3.3 squared is 10.89, and that equals now X over 16. Times both sides by 16, and I get 174.24 grams per mole. There it is. So that was exactly what I just did. So we can play these games of playing around, but I like to go back to the original equation and pop it in there, and that's what I did. So now the question is, what is X? I mean, so you know what nickel, the mass of nickel is, and you know what the mass of C and O is. You could use that information. So to figure that out, because remember how to figure out molar mass is you add up all the individual substance elements in the compound formula. So 58.7 must be nickel, and that's what it is. And then X is, I don't know, right? And it's X times 28, because the CO weighs 28. So you can just solve for X and you get 4. So your formula would be NiCO4. And that's called nickel tetracarbonyl. All right, so now as far as deviations, this is the last bit of our chapter here. Gases under ideal conditions, which is an ideal condition is high temperature or hot and low pressure. But if you put them under low temperature or high pressure, you get some different ideas here. For every 1 mole of an ideal gas, this is kind of interesting. What we're looking at here, this little graph that your textbook gives you, it's showing you that this line here is what an ideal gas would do, even under high pressures, if it would continue to follow the kinetic molecular theory, which is that they don't attract or repel, and they don't take up any space and all that stuff. But that's obviously impossible, because when we put something under really high pressure, and you notice these are huge numbers, the molecular size is going to start taking a toll. It's going to contribute. And you're also going to see some attraction or repulsion. So what's kind of weird about this is what they're doing here is they're saying PV over RT equals 1. 1 what? 1 mole. Okay, well, if it deviates from ideal behavior at all, you'll see a difference. So under high pressure, this red gas, this red line right here is NH3. And so what happens, you put this guy under high pressure, immediately they stick together. And it actually looks like there's less there than 1 mole as far as calculations are concerned. But what happens if you keep on putting it under pressure, then you get repulsion, and that starts to increase. It's number 1 here. It actually up here would say greater than 1. Down here would still be lower than 1. So when it starts to decrease, those are attractive forces rearing their head. And if it immediately just goes above 1, that means that's repulsive in nature. And that's hydrogen gas, by the way. I mean, hydrogen does not like to be compressed. And that's because it just has no attraction for each other, and you can't even force it to. Whereas methane doesn't have much of an attraction, but if you put it under pressure, it'll attract for a little bit, and ammonia will attract even more. But either way, you keep on putting them under pressure, and they will eventually repel each other. So if you had some values, you could actually say, well, I'm going to just choose some values right here. Say I chose values right here, and I chose a pressure right there. And how is that going to deviate? You could just put that huge pressure right here and the same volume and gas constant NT, and you would see that this is now greater than 1. So if it's greater than 1, that means that is now no longer ideal. So as far as why that occurs, this effect of intermolecular forces is because when you increase pressure, intermolecular forces can increase and they can attract each other. Intermolecular forces can become repulsive and they repulse each other. So this van der Waals equation ends up, what that does is it takes that into account. The van der Waals equation looks a lot like PV equals nRT, except it has these correction factors. And those correction factors are this B and A, and they are correction factors for pressure and volume. So the B corrects for molecular volume, and the A corrects for intermolecular forces. So here you have A and B for specific gases. So you might look at just a few of these and you think, oh, wow, why they have different values is kind of interesting, because molecular volume, you look at these numbers, that they're all pretty small, but if you put them under pressure, you have to take them into account. So as far as your fun sheet, on your fun sheet, I think I asked you to do a couple of these, that if you put them under weird conditions, what's going to happen? And a lot of times, if you use PV equals nRT and you use the van der Waals equation for non-ideal behavior, you get similar answers, but not the same. And that can show you the degree of the